Hello everyone, welcome to the lecture 15 of Multibody Dynamics. Today we'll be talking about flexible body simulation. We have successfully completed with 7 weeks of Multibody Dynamics course. And here's a quick recap. We started with the basics of model building and then we simulated the free falling of a stone. We then built a simple pendulum and continued building our final model to finally simulate the motion of an automobile trunk lid using the 4-bar mechanism. In week 6, we concentrated on the higher pair constraints and simulated the cam follower mechanism using the CV-CV joint. In the last week, we covered the topic on contact simulation, which included both theory and a practical hands-on demo for simulating the contact forces acting on a ball bearing. This week and the next week, we shall cover one of the most important topic currently trending in MBD world, which is flexible bodies. So this video lecture series on flexible bodies consists of 4 lecture videos. I have covered the theory on flexible bodies in the first 2 videos and the hands-on demo is incorporated in the 3rd and the 4th video. Please listen to all the video lectures carefully and we can have a Q&A session on the 10th of March during the live webinar. Let's begin with an introduction to flexible bodies. In this chapter, we will cover the following topics. First of all, we will understand the advantages of simulating with flexible bodies when compared to using the rigid bodies in our simulation. Here, we will understand the importance and the purpose of flexible body simulation and why it is very popular in the industry and the research domain when compared to the rigid body analysis. Next, I will show you how we can create flexible bodies in MotionView MotionSolve. It is very easy in this software to create the flex bodies when compared to other software tools, since it has built-in FlexPrep utility which makes it very user-friendly. The FlexPrep tool in MotionView can be used for the following: for generating the flexible bodies and also for converting the flexible bodies to other file types. I will illustrate both the applications of the FlexPrep utility in this demo video. Next, we will see how to animate the flex body modes in Hyperview, which is Altair's post-processing software. This is the software that we used in all our exercises for animation. So we'll be using the same software to animate the flex body modes. We should also learn to swap the existing rigid body with a flexible body for performing a flexible body simulation. In the exercise demo, I will be replacing the rigid lower control arm of an automobile suspension with a flexible body to capture the deformation and the stress and strain effects. In CAE, we should always aim in building models that are very close to the structures in the real world and try to obtain results that correlate well with the test results so that we can minimize the cost of physical testing in the industries. Finally, the analysis that we'll be using in this exercise demo is a quasi-static analysis. So I will give a small briefing on quasi-static analysis before we dive into the simulation. Okay, so let's first understand what is a flexible body. Most of us from the FEA background are well aware of the fact that the finite element models have very high number of degrees of freedom. Hence, it is difficult for the MBD solvers to handle these models. That's one of the main reasons why the FE models take a longer time to converge when compared to the MBD models. Hence, the key fact is that we need to condense the FE models to create the flex bodies. So thus, we can form the definition for flexible bodies. A flexible body is a modal representation of FE model. It is an approximation of a deformable structure used in CAE analysis. It can be used in combination with various CAE solvers to capture large deformation and stress-strain effects on the structure. This data is very useful in various domains such as design, durability, etc. Okay, moving on to the next point, I believe you all would have heard the word superposition. It is basically the net response caused by two or more stimuli. It is the sum of the responses that would have been caused by each stimulus individually. So another way to picturize or understand what a flexible body is by correlating the formation of the flexible body to the concept of modal superposition. This makes it very efficient for the solvers that need to model structures as non-rigid. I will explain in detail how this happens in the upcoming slides. Let us continue our discussion on flexible body and understand its details. I believe all of you would have studied Fourier series in your mathematics course. So you will use that knowledge here to interpret what I will be explaining in this slide. The way MotionSolve determines the deformation of a flexible body to an applied load can be correlated to the Fourier series analysis for periodic functions. Now coming to the meaning of periodic functions. A periodic function is a function returning to the same value at regular intervals. It can be estimated by the sum of sine and cosine functions of varying frequencies that are multiplied by coefficients, illustrated in the figure shown in this slide. So this is a square wave, sawtooth wave, triangle wave, and a semicircle wave. So all these can be considered as the examples of periodic functions. In the same manner, MBD solver will calculate the coefficients for the various deflection modes calculated in the component mode synthesis methods, which then added together produce the resultant deformed shape. Please make a note of this component synthesis method or the CMS method. It is very important and we will discuss this in detail in the upcoming slides of the lecture. Now let us deep dive into the concept of modal superposition. As I mentioned in my previous slide, the idea behind a flexible body is that the final shape can be synthesized by adding a set of modal participation factors and mode shapes. Let us now consider the below example in 2D. The first coefficient or the modal participation factor is 0.7. It is multiplied by the first signal, which is a sine wave. Now, this is added to the second modal participation factor or the coefficient, which is multiplied by the second signal or a second sine wave to give you the resultant signal. So this comes under the domain of signal processing, where you have a primary signal and then it combines with a carrier signal to provide an output, which is a resultant of the primary and the carrier signal. The same concept of signal processing and modal superposition can be applied to the flexible bodies in 3D to obtain a shape. As you can see in the current slide, the images that you see here is of a flexible lower control arm. For instance, a coefficient or the modal participation factor of 0.2 is multiplied with the first 3D shape, which is combined with the second modal participation factor multiplied to the second 3D shape, again which is summed to the third modal participation factor multiplied by the third 3D shape to finally give the deformed shape of the structure. The 2D signals can be related to the 3D shapes of the structure. This is called modal superposition. When I say it can be for any response, when I say shape, it can be for any response such as deformation, stress or strain. Okay, now we have thoroughly understood the manner in which the flex bodies are formed and the concept involved in their creation. But now let's go back to our first statement that I mentioned in my first slide regarding the fact that finite element models have a very high number of degrees of freedom and it is very difficult for the MBD solvers to handle these models. Thus, this concept of modal superposition matters in a way that the solvers only need to calculate these modal superposition factors as shown in the current slide by multiplying with the 3D shape, and that is orders of magnitude less work for the solver than calculating for thousands or 10,000s of nodes and elements in an FE model. I hope now you realize the importance of the flexible bodies in the MBD world. Now, let's concentrate on the two key aspects in the modal superposition. They are the number and the maximum frequency of the mode shapes. Increased modes and higher frequency enable more curvature in structure in responses such as deformation, stress, and strain. If you can see in the images, the one on the left has low frequency, which can be correlated with the large wavelength in 2D, hence resulting in a broad curvature, while the image on the right illustrates the high frequency shape, which can be correlated with small wavelength, resulting in a tight curvature. Please note that the stress or strain generally have higher curvature and require more modes to capture their effects when compared to deformation, which can be captured with lesser modes and lower curvature. Okay, now let's discuss regarding the applications of flex bodies. Why was there a need for the evolution from rigid bodies to flex bodies? It is due to the following main reasons. One of the most important reasons is that the flex body can capture large deformations that we usually see in the physical world more realistically when compared to the rigid bodies. So, the CAE results from the flexible body simulation will be very close to the actual test data. The second reason is to improve accuracy in load predictions. This plays a major role in FEA since the loads calculated from the MBD analysis will be used in the FE models to conduct further analysis. Hence, it becomes very important that the predicted loads from the MBD models are highly accurate to support the FEA work. The third reason is that it is possible to capture the stress or strain distribution in a body using the flex bodies, and it is not possible by using a rigid body. This is one of the basic requirements in the CAE world. It is not just sufficient if we compute the forces, torques, accelerations, displacements at various locations, but it's very crucial that our model has the capability to deliver the stress or strain results depending on the user's request. This is possible only if we build our model using the flexible bodies. Moving on to our next point, flexible body helps in generating loads needed for fatigue analysis. And as I mentioned earlier, these loads are highly accurate, which will avoid any errors creeping into the FE results. Okay, now let's move on to the next point. If you guys remember, in chapter 7, we dealt with the redundant constraints. So apart from using J-prints, flexible bodies also help in removing redundant constraints. Lastly, the flexible bodies provide an excellent trade-off between accuracy and simulation time. The degrees of freedom are reduced drastically when compared to the FE models, thereby yielding faster results. You can compare that by seeing these two illustrations on this current slide. Now consider the figure on the right hand side of the slide. It represents the cylinder of an engine with a piston, connecting rod, and a crankshaft. For instance, let us consider that we want to compute the stresses in this particular connecting rod. We can only get this information if we model the connecting rod using the flexible body rather than a rigid body. Also, moving further, if we want to capture accurate forces exerted by the piston on the cylinder block, then we must make use of the flexible bodies rather than the rigid bodies. This term, interface nodes, plays a very important role in the flexible bodies. So let's understand what interface nodes are. The flexible bodies connect to the multibody dynamic system through the interface nodes. There is no rule that all the interface nodes on the flexible body need to be used. However, any node with a force or any kind of constraint must be an interface node. The outputs such as displacement, velocity, and acceleration need not be an interface node. So what I'm trying to explain here is that if there is any node on the flexible body with any kind of constraint or force associated with it, then it will be tagged as an interface node. Okay, Now let's move on to another important topic in flexible bodies, which is the component mode synthesis methods or the CMS methods. I had mentioned regarding the CMS method in my previous slides. Now let us discuss about it in detail. There are 3 component mode synthesis methods supported in OptiStruct that will reduce the FE model to a set of orthogonal mode shapes. Basically, the CMS method is used to condense a FE model into a flexible body. There are 3 CMS methods. They are the Craig-Bampton method, the Craig-Chang method, and the Craig-Bampton geometric stiffness method. Now let us discuss about each of these methods in detail. In Craig-Bampton method, there are 2 sets of modes that are computed. First, the fixed interface constraint static modes are calculated by applying a unit displacement at each interface nodes in each degree of freedom individually while leaving all the constraints active. Second, the fixed interface eigenmodes, which are calculated with all the interface nodes constrained, where the number of modes is specified by the user. So finally, both these set of modes are orthogonalized, producing the modal matrix of mode shapes which will represent the flexible body. Now, let's move on to the second method, which is Craig-Chang method. In this method, again, 2 sets of modes are computed. They are the inertia relief attachment static modes, which are computed by applying unit displacement on each of the interface nodes in each degree of freedom individually, while leaving all the interface nodes free. So this is the main difference between the Craig-Bampton and the Craig-Chang method. In the Craig-Bampton method, unit displacement is applied at each interface nodes in each degree of freedom, leaving all other constraints active. And in Craig-Chang method, the interface nodes are free when the unit displacement is applied. When calculating the static modes, the model is mathematically constrained by inertia. Hence the word inertia relief. So, to produce structural deformations, the mode shapes will be required for calculating. So these are the first set of modes created by Craig-Chang method, which are the inertia relief attachment static modes. Now, coming to the second set of modes created by the Craig-Chang method, and they are the free eigenmodes. They are computed without any constraints on the body. Now, the first and the second set of modes are again orthogonalized, producing the modal matrix of mode shapes that represent a flexible body. The third method is the Craig-Bampton geometric stiffness method. It is nothing but an extension of the Craig-Bampton method, but it further includes the effect of non-linearity, the geometric non-linearity. So, thus I have explained the 3 component mode synthesis methods that are supported in OptiStruct. In the next video, I will explain the applications of these CMS methods. Thank you.